My name's Heather Calando. I'm a senior editor for Plastic Technology Magazine, and welcome to today's webinar, sponsored by Fortify, Concept to Molding Parts in 4 days, Raising the Bar for 3D Printed Tool Performance. Our presenter today is Ben Arnold, Vice President of Business Development, Fortify. Ben has decades of experience helping manufacturing companies implement new capital equipment technology and has been on the forefront of several key 3D printing innovations, serving the injection molding industry with polymer and metal 3D printing. Ben holds a BSME from WPI and MBA from Northeastern University. All right, Ben, it's all yours.
Thank you, Heather, and thanks everybody for jumping on with us today. Let's take one last minute to admire this great shot of our printers here, and then dive right into the program. The agenda today, we're going to give a quick talk about Fortify, help understand who Fortify is as a new company in the 3D printing game, our application focus on 3D printed injection mold inserts. Yes, you can mold plastics in plastic molds. People have been doing it for years, and we'll talk a little bit about then what we're doing differently in this space to sort of, as the title said, raise the bar on performance. Some key difference between 3D printed, and these would be 3D printed polymer tools and traditional metal tools, so traditional CNC machined tools. We will not be talking about 3D printed metal tools today, but polymer-based 3D printed tools. We'll then cover a case study, the actual concept of molded parts, an actual project that we did. We are joined today by our ACE applications engineer, Ben MacDonald. And so he'll take over for that section of the talk, and then a couple more success stories, and then some Q&A. So really look forward to getting through the content here so we can get to your questions. Quick overview: Fortify is just over 4 years old. Started in 2016, a spin out of Northeastern University right here in Boston. Started our accolades with the Mass Challenge win, which is a local competition for startup companies. The company received seed round funding in 2017, launched the digital tooling platform, the technology we'll be discussing today, in 2018, and have worked over the last couple of years through another round of funding to the point where we're actually delivering our first printers this summer to customers all around this injection mold tooling application we're discussing today. We've been recognized around the world for the innovative work we're doing, and probably the most important recognition and award is from the funding community, which have been great supporters of, I think, 3D printing, the additive manufacturing industry overall. But Fortify has really great financial backing, and actually will be probably raising additional money soon. Even given all the COVID situation and everything going on, we're charging ahead through it all. In fact, in the middle of COVID, we moved to our new headquarters here. I don't know how many people on the call here are locals or have been through Boston, but if you've ever been to Boston and traveled north to New Hampshire or any of the northern suburbs of Boston, you'd pass the iconic Hood Milk smokestack in Boston. That's a new renovated office park area, and Fortify is one of the anchor tenants in that complex. So we're real excited about our new home, and have actually been revisiting it lately as restrictions loosen up in Boston. So that's a quick view of Fortify from sort of a company standpoint. Our technology platform, we're what we would call a full stack 3D printing company. So that's hardware, software, and materials. We do partner on all three of those fronts, on both the hardware, software, and materials. We're not inventing everything from scratch. We're working to advance the state of the art and leverage existing technology where possible. So our printer is based on a proven DLP engine. We'll talk a little bit in a minute about the specific modules that Fortify has invented and our IP. Software, again, we use partners where appropriate. And on the material side, we partner with global companies like Henkel and others for the base resins, which we then move forward through our process and applications engineering to figure out the real core value of Fortify is the premise being neat polymers. The polymers, no matter how great the companies are, the neat polymers are going to always be limited in their material properties. And we use a trick or a technology or an approach that the injection molding industry is quite familiar with, which is engineered additives, whether that be in the injection molding world, it might be carbon, short chopped fiber carbon or glass filled or other engineering additives added to the material prior to molding in order to impact the material properties. So we take that and apply it to additive, the first company to do that in the photopolymer space. And in order to do that, we invented a couple of key new pieces of intellectual property, one being our continuous kinetic mixing module, which allows us to introduce the functional additives. In the case of the mold tool application we're talking about today, it is a ceramic fiber that has been pre-treated to make it magnetically responsive. We mix that with the base resin, and that's we'll talk in a minute about with the material properties that we achieve. But in order to have those additives in the material, we have to keep them in constant motion so they don't settle out or clump up or cluster up. We need a uniform distribution of the particles. That's achieved through our kinetic mixing module. And then the other module is our flux print magnetic alignment. So now that we have the particles in, or the fiber in a homogeneous suspension, we can apply magnetics to it and to get that to line up in the way that it's most advantageous. There's a full process video that I would encourage folks to watch at our website. This is a theme that will come up several times through the presentation. There's only so much we can cover quickly to get to the Q&A today, but the in-depth description of everything we'll talk about today is on our website at various places. It's not easy to navigate our website, so that's 3dfortify.com. But one thing I'll show here, this is an actual video of magnetic alignment at work, as we can see the particles here, or fibers, all reacting to a magnetic field and aligning. Here we show them all aligning in sort of a vertical fashion from random, when in the actual system, we're able to align particles vertically, horizontally, really in 360 degrees of rotation of the fiber, so that we can align fiber so that the materials carry stress in the correct orientation. So this is a breakthrough for any kind of fiber reinforced material. As you know, in injection molding, when you mold fiber reinforced parts, the fiber always aligns with flow. We're able to overcome that and have fiber aligned at our wishes. So that's the bit of the core technology of Fortify. Now we'll shift focus to this application on the 3D printed injection mold tooling application. So, why consider 3D printing tooling today? Why have people considered it and tried it for the past, as long as I've been in the 3D printing and additive manufacturing industry, about 16 years now? Whether it's polymers or metals, the ability to quickly produce a tool has always been of interest. The two big drivers are fast turnaround and lower cost, and dramatically faster and lower cost. When we can have molded parts in 3 to 6 days versus 3 to 6 weeks at the prototyping scale, and talk about tooling costs at $300 to $600 versus $3,000 to $6,000, those are big breakthroughs. I wish we could say we could do faster turnaround, lower tooling cost, and better results. I think that the third holy grail is a tough one, and we'll focus on exactly what that means. But the focus here would be short runs, the ability to quickly get molded parts in your hands. And then there's 8 more reasons that customers have shared with us. These aren't our reasons, but as we listen to customers, why they're interested in exploring this. Here's a list of the full top 10 reasons. It's always great to have a top 10 list. I'm not going to go through the top 10 list here, but again, on our website, we have them listed, and it's always good to see which of these might resonate with different customers, whether it's custom molders that are looking to service their customers over a wider range of the project, from cradle to grave, you might say, early stage prototyping through volume production, or whether they're captive molders working to support their in-house engineering departments with ever faster product development cycles. So that range of reasons why, again, all available on the website. So back to the advantage of Fortify. This is kind of a general statement about how mechanical properties are enhanced with our fiber reinforcement technology. So we can see a chart here, some of the other materials that we'd see on the market. The Somos Perform material, which is certainly another player in the injection mold tool space. The Formlabs high temp resin, and then the Fortify neat resin. That would be the base resin that we start with, unreinforced. And we can see here on the chart how our fiber reinforcement bumps that performance up. So typically we're seeing, this is across the board, not just in the tooling application, but a doubling up to 50 to 100% in tensile strength, stiffness increases of up to 5x, wear resistance of 100%, so twice as wear resistant. Again, that definitely plays a role in the tooling application. Fracture toughness, the ability to sort of withstand continuation of cracks once they might get started, and heat deflection temperature, a big driver in the injection mold tool application. If we look at the specifics of our digital tooling, this is the material that we use for all of our tooling applications. One material set supports all of the molded materials. We have a list of materials that are qualified for molding into this material, but we would use the same material on all molding applications, and it's this ceramic reinforced digital tooling. Again, the spec sheet available where else? On our website. But the key properties here being strength, stiffness, and heat deflection temperature are 2 to 3x higher than competitive materials. And what that means in practice is this is an actual use case of a Fortify tool. After 100 shots, the key test here was how these extruded features would hold up against a competitive 3D printed tool where the extruded features failed on the first shot. Same molding conditions, same mold material. I believe it was ABS was the material that we were molding in this case. And the point that I think is interesting to make here is that although we have a significant breakthrough in tool performance, the one on the right, that tool, that material has been used successfully in lots of molding applications. I guess I've been doing this a long time. I sold that material into this application, and we know that people can get good results out of it. If you can get a material that's got these kind of additional performance characteristics, how much further can we take the application? I think that's the theme of the webinar today, is raising the bar. Another way that we've raised the bar is by bringing actual molding technology in-house. Every 3D printing company has 3D printers in-house. We have a full molding lab as well in our Boston facility, so we don't have to wait and go on site and steal time on customer machines to learn about how our molds are performing when we want to try a new formulation or a new geometry. We're able to do that right in-house. So we're able to support customer projects as well as our own development projects. Some of the key differences between 3D printed and traditional CNC tools, whether they're aluminum or steel. One would be best fit on part selection. You're really no limitations on part size when you're using metal materials. With 3D printed tools, we like to stay in sort of a 5-inch longest part dimension and below. We've done some pretty big molds. This is not a hard, fast rule, but a best practice, I'd say. What that does is it lets us turn molds around faster. As 3D printed molds get bigger, they take longer and cost more money. Larger parts run at higher pressures. We like lower pressures. We like higher temperatures, lower pressures, and also smaller shot sizes in smaller parts, which means there's less heat to dissipate. And we'll talk about that in a minute. So one key point there would be parts selection. Materials, again, you don't have to take too many notes here. All this information is available on our website and then our molding guide. But we look at material as classes. We would say there's easy materials, more challenging, and most challenging materials. In the easy materials, we're looking easily at hundreds and hundreds of shots on our tools. As we move up through both more challenging materials and more challenging designs, the number of shots that we're able to sort of guarantee or stand up to goes down into the 50 to 100 shots with maybe a polycarbonate, and a glass-filled nylon, 20 to 50 shots would be reasonable expectations for tool life. All this with tolerances around plus or minus 5 thousandths or better. Mold frame design is an important component of the process here. Part of the whole idea is to get molds quickly produced and on and off of our tools. We've worked with PCS on a specialized set of equipment from their FITS or FITS product line to develop a tool that has different pocket sizes. You can see in the frame here, this is a relatively small mold, but if we were to remove this core or spacer plate, we could get a larger tool in there. We could also remove the center block and use the full pocket for larger parts. Adjustable side rails, these clamp or these socket head cap screws here move this rail in and out, so we're able to clamp parts in, not be able to skip a step of machining the side rails. And this is a design that is available to our customers. If anybody's interested in how we design this, we definitely have no problem sharing that design. We don't give you the full frame, but we give you the design to replicate on your own. And then the final piece that I'm going to talk about here is cooling and cycle time. A big difference between our tools and metal tools would be the cooling. Our tools do have a lower heat transfer than they do than metal tools would. So that means longer cooling cycles and longer molding cycles overall. There's no need to water cool these molds. We just simply use compressed air on the surface of the molds. One of the benefits is low heat transfer is it keeps the surface, the heat at the surface of the mold where it can be easily removed with compressed air. And the key to getting good consistent results is to tie the compressed air into the automated cycle of the machine, right? If you want to auto cycle parts and get the exact same molding conditions for all parts, we definitely recommend tying that into a solenoid valve so that we're applying the same cooling on each shot in a run. So that was a very quick run through of some of the highlights. For a deeper dive of all of the sort of best practices and guidelines for use of our tools, the guidebook that's shown on the screen here is available for a download from 3dfortify.com. There's a real treasure trove of information out there. So we're going to now move to the next segment, which is to talk about an actual project, concept to part in 4 days, a PPE response story starring, of course, Fortify. I'm going to introduce it here and then hand it over to Ben MacDonald, the applications engineer who actually carried this project through cradle to grave. Our team has worked diligently on PPE projects. This is one of, I think, 4 projects that we completed for local companies that were all busily working on PPE projects. But the ventilator project Their mission was to keep up with demand for ventilators for COVID patients using refurbished tools like CPAP and BiPAP machines. In order to use these machines, they needed to build in some additional safeties, and that safety is that the T valve, the T fitting that was used to install a pressure sensor was the project that they brought to us. So, Ben, I'm going to hand it over to you now on this next screen here, and you can talk a little bit about. Do you want me to stay on this screen or go right to the next?
You can head right over to the next one. We'll get into this. Alrighty, so to start off this project, we were given two separate designs, and we weren't sure which design they wanted to move forward with. So instead of pausing and wasting precious days, we decided we were going to design an insert, or rather two separate inserts, to create the two different geometries in order to start moving forward with the project, even though there was some uncertainty. And we did this in order to not make two different molds. So that's saving us time, that's saving money for both us, but the customer too. So another requirement on this project was there are two sealing faces on this part. So there is a sealing surface on the inner diameter on the left end there, and then on the outer diameter of the right side, there's another sealing surface. So those will seal with a specific filter. The name's escaping me right now, but they need to create a tight seal. So we had to move the parting line on the part off of those surfaces in order to create that good seal. So this led us to create some pretty interesting inserts that we'll get into. And then we also had to create another custom insert for the internal thread at the base. So as I'll get into in these next couple slides here, there was a great deal of design work for these different inserts. But a quick overview of our design process for these inserts. First, we'll start out modeling the part into the actual core and cavity of the mold halves. From there, we'll design our inserts around this part, and then we'll cut these inserts into the core and cavity of the mold in order to create our final geometry. With this particular part, we ended up going with 5 separate inserts to fully create the part while satisfying the different customer requirements of being able to mold those 2 unique parts, as well as removing parting lines. So if you look on the right-hand side of that image with the part, that is the unique insert that we created, and that allowed us to move the parting line off of that outer diameter and rotate it essentially 90 degrees onto a surface that was acceptable to have some sort of a witness mark on. And now we can dive into the thread insert. This insert was a nice challenge for us because we have a thread at the base of this insert, and then at the very top of the insert, we have features that constrain the rotation of the overall insert. So we had to design this as 2 separate pieces. This was really a great fit for us because this isn't something you can just get off the shelf. This is a custom machining job, so that's long lead times, it's expensive if you're to go a traditional route, whereas all of this different complexity was free of charge for us to add into this design. So it really highlighted the benefits of our technology well. So the overall timeline for this project, day 1, we got through the mold design, designed the inserts as well, and we were able to get this printing overnight so that when we came in the morning of day 2, we had printed molds, we had printed inserts ready to go through their post-process, so the cleaning and post-processing steps. From there, we came back in on day 3. We were able to get everything fit up to our mud frame, and by the 4th day, we had molded parts ready to go for the customer. And this is a quick highlight of the process we use. So we molded the part out of Polypro on our own internal mold press. and we were able to do so with pretty forgiving pressures and settings for our mold tool.
Awesome, thanks, Ben. So if you have questions on this specific thing, we have a few more case studies to run through, and then in the Q&A session, we can refer back to these slides if we need to. But I think it's a really great example of what can be done now. Having a guy like Ben MacDonald is really another key bit of getting this done in 4 days. It's not just having the tools, but having a skilled operator. So that's a theme that is important to keep in mind. Some additional customer success stories, just to show the range of industries and companies that we've worked with. This was an automotive application in a nylon and glass-filled nylon. So the goal here was 25 shots of glass-filled nylon. We started off with a neat nylon 6 and got 50 shots of nylon 6 and another 50 shots with the glass-filled nylon. So there's 100 shots on that tool. If up top we show the difference in what had been quoted for metal tool. Again, to do this prototype run, this was something the customer needed to make these parts in order to prove to their customer that their application was going to work. So they only needed 20 shots. A metal tool to do this job, where they were quoted $8,000 and an 8-week lead time. Our tool, $500. The $500 would be the cost for this tool if you owned it. So tilt the scales a little bit there in complete honesty. But the numbers we present here for cost assumes that you own the tool and you're not buying that tool from a third party, but you're printing the tool. So 5-day turnaround on a project like that. Those molds take a little longer to print, and that's a set of results that we got there. An industrial application here. These are I think some pipe clamps. In this case, we actually sold the tool, so the $1,300 was the cost to a customer that bought the tool from us. The metal quote on that case was $2,000 for an aluminum tool. In 28 days, we were able to get a tool turned around in 3 days. This was run by the customer on site at their facility. Their goal was 100 shots, and we got to 400 shots before shutting the project down. It was a win. Again, these case studies are also on our website. Textured molds. This was an interesting case. Very small mold in this case, but the trick was that we needed to get this texturing on the outside. 3D printer, as long as the 3D printer can handle the texture, which we can get to pretty fine resolution here, to Ben's point, there's no extra charge, no extra work to print texture as it is to print smooth. Whereas EDM would have been required to get a metal tool to have this kind of a pattern in it. So we've done some really interesting additional work on patterning that if that's something of interest to you, bring it on. This case here is more about repeatability. No, I don't think anyone was surprised with the life of the tool. We got 300 shots. That was all that this tool was subjected to. This company had also tried 3D printed tooling on this application. Their concern was less about tool life, but more about repeatability. And this is where the heat deflection temperature and the stiffness of our tools comes into play, where they molded the 300 parts and they did very extensive measurements. This is just one of the measurement characteristics. They measured 13 different points and found that our tool on 2 runs, this was run last summer, they ran it once in June and again in August, and we on 13 measurements, I think we were in spec for their QC standards on all but 2. And those 2, we identified a modification to the tool that we could have done to fix that out of spec as well. So that's another point that often gets missed with 3D printed tooling. The question is always how long will it last? But an equally important question is how good are the results? How repeatable and consistent are the results? now that we finally get to the point where we can make a decent sized quantity of parts. And then another final test was in metal injection molding, which is a very demanding application. It's a abrasive metal polymer slurry that's molded into parts. In many ways, it's similar to the traditional injection mold process, but the feedstock is just much more abrasive. And again, working with a company that actually lets us say their name, which is Alpha Precision. And again, in this case, they also had tried other 3D printed tools without success, and our tools held up to their process demands. So that's another consistent theme. Is we've worked with a lot of companies that have already tried this application, and we're very excited to see, have we in fact, we claim we've raised the bar, but have we? So that's the content here, and so now it's like, what are the lessons learned? What have we learned? What have I learned over the years of doing this application that have been reinforced over the past year and a half with Fortify? Is that this is a tool that we're presenting here, that when we have reasonable expectations and you make this rapid molding a valuable component of your business, use it on a regular basis and gain the expertise to be able to envision a solution like Ben MacDonald could on that ventilator component, how the inserts could be worked and how all those parts could be 3D printed. You're able to build yourself a very compelling competitive advantage, because you can go to your customers and say, we can turn around projects like this. I wish I could say it was as easy as purchasing the equipment and all of a sudden you have those capabilities. But it's a matter of learning the technology, embracing the technology, building that competitive advantage, and then putting it to use. The converse of that is that this is not a great fit for fire drills. We get calls many times from molders like, hey, we got this hot project, and if we wait our normal 8-week or 6-week lead time, we're going to lose the business. So now seems like the perfect time to try out your technology. And the watchword here is the right time to try out our technology is before you're in a fire drill situation, so that you can respond quickly, as we demonstrated on the ventilator project. So how do we help companies do that? And that's really the next steps. What we've developed at Fortify, again, based on years of experience with helping companies adopt this technology, is we call it our onboarding program. We work with molders who fit that category, where they have either already a heavy load of quick turn projects, or anticipate that could be a strategically important piece to their business. We work with side by side to transfer the knowledge. We ask for a small commitment, and that we work through 2 projects, start to finish: mold design, frame design. How are we going to get the tools on and off of the press quickly? We share everything we have to bring to the application with you. Ben and a couple other applications engineers will get involved to work it through. And from there, of course, ultimately our goal is to sell machines. We are in the equipment business where we do sell inserts, we do run complete molding projects, but the core of our business is to sell these beautiful Flux 3D printers that you see on the right side. And so the goal is, again, is to help people learn how to use the technology so that it can be a logical addition to folks' business. That's what we had, and I think we got through it just as expected, 35 minutes, exactly what the plan was, and so that we can have plenty of time for Q&A. So we're here now to answer any questions you may have about the technology, the materials, the experience of that ventilator project. Just don't ask us for a ventilator.
Okay, great. Well, thank you, Ben and Ben. Yes, if you all have any questions, you can type it directly into the webinar interface. And so we have some right now, so we'll get started. If I'm interested in presenting or sharing this information internally, is there a way to get the copy of the slides?
Yeah, I'll field that one. So you have my email address right there, benarnold@3dfortify.com. Just drop me an email, and I'll be happy to get you a copy of the slides. The deck here is pretty heavy as far as it's a big file, but we'll find a way to either skinny it down or get a copy to you. The other Ben, by the way, his email's not there. He's just Ben. Ben MacDonald was first, so he got Ben at 3D Fortify. I'm Ben Arnold at 3D Fortify.
Okay, great. Does the orientation of the fibers affect the structural and dielectric properties of the printed parts?
The orientation of the fibers. I'll take that one again. The orientation of the fibers definitely impacts the strength of the part. We have some other application space where dielectric properties are of great interest. And so we can speak to that and probably in a different forum easier. I honestly don't know. We've never measured in the tooling resins and the specific ceramic reinforcement and the magnetics that we use in there. My sense is that they would have not a good impact at all on dielectric properties, but we've not measured them. The tooling material was designed specifically for the tooling application, and I think about 99% of all experience we have with that material would be for this application where dielectric is not measured. So it's a long way of saying I don't know.
Okay, have you compared your reinforced inserts to printed, sintered metal powder inserts with similar turnaround times and cost?
So I've worked across both industries, in metal and plastic, so I'll field that as well. I don't. Again, the short answer would be I'm not aware of an ability to do something with a similar time and cost range when we're talking metal 3D printing versus polymer 3D printing. Metal tools are going to hold up better over the long run than polymer-based tools in almost all cases. So there's definitely a compelling advantage to using metal. I'm certainly not aware of a technology that would be able to produce molds with a surface finish that would be suitable for molding in this kind of 1 or 2 or 3 day type of a turnaround. Typically, there's some kind of significant post-processing, either machining or hand polishing, that will be required to get a finish on a metal tool. If somebody knows of something like that, you got my email there. I want to be aware of it, but I guess my answer right now would be that I think metal 3D printing definitely has a compelling use case in the injection mold tool application, but the fastest and lowest cost turnaround I don't think is it.
Okay. Okay, so this is a little bit of a long one, so let me know if you need me to repeat any part of it. So for our boat production, we have used our first ever 3D GF nylon printed insert to alter an existing fiberglass mold dimension. It worked okay, but we have had minor difficulties with the epoxy sticking to the insert. What would be the most suitable printed material, and have you ever experimented with 3D resin part longevity?
You want to try that one, Ben?
I can give it a shot. I don't have a great answer for it, to be honest, but it's a 3D printed glass-filled nylon. So I think there should be a match between whatever adhesive you're using. So I think it would be just using a different adhesive that has been proven to work with that printed material should be the solution there. But We'd have to take a closer look at the actual use case for.
Yeah, that would be my answer. I think is that, yeah, I think it's gonna be hard to do that one just from a spoken word. But again, we have our email address, Ben Arnold or Ben at 3dfortify.com. If you want to send some drawings, or we'll do our best to try and tackle it, and maybe there's a mold release type of a solution that could be helpful on this one. But I'm not getting a clear picture of the clear enough picture of the problem to give an intelligent response. But please email us.
Perfect. Okay, great. What is the smallest resolution for the textured mold?
Yeah, I'll tackle this one. So technically our pixel size is like 75 micron. So our smallest resolution is going to be 75 micron. That's very tough to actually see with the human eye, but anything on the order of 100 to 300 micron, I mean, there should be no problem printing or actually realizing the results of that printing, so being able to see that resolution. But we can get all the way down to 75 technically.
Yeah, my answer on that would be is that typically it's going to be resolution that you're going to see when you're holding a part in your hand and looking at it. They're going to look great, and if you look at them under a microscope or even a strong magnifying glass, you'll see the tells of the 3D printing. Again, just perfect transparency. And Ben MacDonald's eyes are probably a little sharper than mine, but that's a much more of a sort of a qualitative answer, I know, but I think it's maybe a useful piece of guidance.
Okay, can you comment on how you change fiber orientation according to anticipated stress in various portions of the inserts?
Yes, I'll take that. So most of the stress in the molding application is going to be either during the compressive cycle or really more so during ejection. So the stresses that we're most interested in would be like when the plastic is flowing in, we're able to see it sort of against sidewalls and standing features, and we have to balance that against those same standing features are going to have stress during ejection. And usually the ejection stress wins. So the philosophy we use is typically around reinforcing the part to withstand the stress of ejection on tall standing features, which, as it turns out, is not such a complicated problem to solve, right? We pick the build orientation and orient fibers normal to the build orientation for those standing features. And sometimes, again, just a little bit of an aside here, sometimes we'll take a mold where we'll have like really high aspect ratio extrusions and recommend like a hybrid design where we might use a steel rod or an insert or a machine component in where there's a particularly vulnerable extrusion or standoff or high aspect ratio feature. Does that help? Hopefully that was a good answer.
Okay, what is the max bed size of your largest printer?
Go ahead, Ben.
Yeah, all right. So our max print size, that's going to be, it's roughly 8 inches by 4.5 inches by about a foot tall. But we try to more so when we're like printing mold inserts, we try to fit the mold inserts more for the part rather than just think about what the maximum size we can print.
Yeah, so the short answer is 8.5 by 4 by 12 would be the maximum size of an insert, and then you want to have about a generous, let's say, a 1/2 inch of clearance of mold around the part, right? So the molds are always going to be bigger than the part.
Yep.
But we do use the machines to print parts as well. I mean, we're talking about mold inserts here, but the beauty of a 3D printer is you can do lots of things with it. But that it fits well. I think the size of the printer fits well with where we would say our sweet spot of our molding application is. We can certainly print molds and mold parts that are significantly larger than the sweet spot mentioned of 5 inches. But it would, again, every technology has a sweet spot. Sweet spot means where the technology is most comfortable, the results are best understood, etc. Again,
have you done any
specific questions and specific geometries? It's hard to answer all questions in a forum like this, but we're certainly not shy about addressing questions. And if it's something that's outside what's not possible, we'll let you know.
Okay, great. Have you done any EBM bottle projects?
Could you repeat the question? It was EDM what projects?
Yes. Have you done any EBM bottle projects?
EBM bottle.
Bottle, was it bottle?
A bottle, yeah, BOTTLE.
EDM bottle applications. I'm not sure I'm understanding the question. EDM would not work so well. Like our material would not. Oh, EBM.
EBM,
bottle.
Yes, EBM bottle.
I don't think we've done anything like bottles with collapsible cores. That the biggest challenge whenever I hear about a bottle application with injection molding would be how you're going to get the core out.
Well, that's blow molding actually. So you're using air.
Yeah, right.
So there is no core there.
Right.
No, we have not done that to date, but I don't see any reason why our technology.
I'd have to see what. I'd like to see a drawing of an EBM bottle, and then we could. Then I can. I'm just not sure what it is. So.
Mm-hmm.
Okay. Is the ceramatic additive mixed at the machine, or does this come compounded? Are there any limitations on base resin, or basically any resin being used? So ceramatic additive mixed at the machine, or does this come compounded? Are there?
Yep, I got that one. So in this application, the material does come pre-compounded from Fortify. I know we show in the picture that you can mix on the fly. That's a separate, in this particular application, what works best is pre-compounding the material so it comes to you as, simple lock and load type of an apparatus. The second part of the question about, is it an open platform, like can you just use any materials? And the answer is a little bit of a complex answer there. The short answer is, especially when we talk about the use case of additives and magnetic alignment and things like that, would be no. Again, and that's not a matter of us trying to control the supply chain as much as it took our material scientists 3 years to figure out the whole process of treating the fibers and compatibilizing the whole mix. And so offline, if somebody wants to talk, I mean, we're certainly wide open-minded to the idea that there could be other use cases for our core technology, and we're very interested to explore those with others, but we're not like presenting to the market, hey, here's a platform for your experimentation with fiber reinforced materials. It's a tricky kind of a thing to get right. We certainly didn't just luck into having this combination of fiber and base resin. So again, it's a kind of a complicated answer. We're open-minded, to working with folks to extend this application or explore whole new areas of application for sure. But we don't. It would be a lot to bite off for a customer to try and develop that.
Okay, what is possible for cooling lines in the mold inserts? In the webinar, the comment was air cooling. In dialogue with Ben Arnold, we discussed insert cooling lines. What is possible?
Do you want to take this one? Or?
Sure.
Okay, so we've actually, the material properties of our material, the thermal, like the coefficient of, oh God, I'm drawing a blank here, but heat transfer coefficient.
Thermal conductivity.
Thermal conductivity, heat transfer coefficient, it's very low for our material. So the benefits of cooling lines really would be kind of minimal at best, based on like what the calculations show, where if once the heat gets like deposited on the surface of the mold, basically, so we can pull it away pretty quickly with this air, where it doesn't sink into the part too much because it can't conduct through the part very well. So we've found that just using air on the surface and removing the heat before it gets into the mold really works the best for cooling our molds.
Yeah, we have no problem if somebody wants to try the cooling. We just haven't had success or haven't seen an impact of it. And whereas the compressed air across the surface works really well and is very easy to implement.
Okay, would you also see a possibility of creating mold inserts for smaller blow molding applications?
I think we've not done it, but I don't see any reason why we wouldn't. I think most of the blow molding applications I've seen, and I'm by no means an expert, have just been fairly large in size. But yeah, if there's blow molding applications that fit our size, then we'd love to take a look at it.
Okay, is it possible to build 3-plate molds with this technology?
3-plate molds. Ben?
Yeah, so you can build a 3-plate mold with this technology. Typically, we prefer not to, just because it's easier to, instead of using 3 plates, we'll create inserts to mimic what that 3rd plate would be doing in terms of the potential undercuts that you might see. So we've just found it's easier to use inserts for that purpose, but there really is nothing stopping you from doing a 3-plate mold.
How easy or difficult is it to change the orientation of the fibers in the mold if one found the first iteration of a mold design had a weakness?
You mean to reprint the mold and with different orientation? Not complicated. I think hard to describe over the phone, but I think would be not so complicated.
Are you using a mold release with your inserts?
Yeah, so that's part of our bring up process actually, where we make sure we're using pretty generous mold release while we're bringing up the part. Once we are filling out our part, we'll only apply mold release if we see the plastic is sticking in a certain area. Otherwise, we'll kind of let the mold continue to cycle as is and try to maintain consistency from shot to shot. And it's kind of a material by material basis where some materials might release a little bit better than others.
But it doesn't hurt the process.
Does
It
not
may hurt the consistency of the process if we use it like every fifth shot or something like that, right? The shot right after the release may be a little different than the next.
Yeah.
But it doesn't hurt the mold.
Okay, yeah, it looks like we just had time for a couple more. I'm just looking. Let's see. Okay, assuming we find a fit for our product mix timing needs, but don't have the desire to bring it in-house, are there any service bureaus that deploy this technology we could access as a bridge?
Yeah, I'll field that one. So the answer is today, I think we've said a few times that we're just rolling out our machines now into the field, and the early adopters tend to be more like captive molders. But we are working with some custom molders, and those custom molders have definitely professed an interest in not only using the technology, but making available as a service as well. So today, I would say there's no place to go and third parties to buy our tools today, but that will definitely evolve, I think, as we start to hit, certainly by this time next year, there'll be places to go for that. So we at Fortify are interested in working with companies because we will help cultivate that knowledge of our tools, and then sort of have a built-in customer base for custom molders. If anybody's out there listening thinking that maybe a tool like this would be good for them, we definitely get plenty of inquiries from people who want to use the technology but don't want to invest. So again, long answer, we envision a robust market for folks that would want to use the tools, and good business opportunity for people that want to buy these tools and sell their excess capacity. We don't envision ourselves being in the quick turn tooling business. We want to sell machines. That's our business.
Okay, for the fiber enforced filament, how is the fiber incorporated to the polymer matrix? Is it continuous fiber with pultrusion or chopped glass with regular extrusion?
It's chopped. It's actually not glass. It's ceramic in this case. It's a specially sourced, very short fiber, very short, very high aspect ratio ceramic short fiber.
Okay, have you ever tried sectionalizing a mold?
Sectionalizing. We've done lots of insert work. Sectionalizing to make big molds? I'm not sure what the...
I think that's what it sounds like, or putting 2 or 3 inserts together to make one larger insert. And that's not something we've done, but I've been hoping to get a project like that for a while, actually, and I think we would do very well with it, but we definitely have to take a closer look at the project to know for sure.
Yeah, I think if we sectioned it and then used an appropriate pocket to sort of hold things together, some good bonding agents and mechanical reinforcement, I think we'd probably do well. I gotta be careful now. We're going to come back with some section part for a 4-foot-long glass-filled nylon part.
I'll do that in my spare time.
Yeah. You have, again, the email address here, the website is here. Any kind of detailed question like that really begs like detail, right? And we're all engineers, so it's like, show me a drawing, show me a part, help me understand the application, and then we can respond to it. But we've not done sectional molds, but seems like a logical extension.
Okay, great. Well, we're at the top of the hour, so I'd like to thank Ben for the great presentation, and Fortify for sponsoring today's event, and all the attendees for joining us. So you will be emailed a link to a recording of the presentation, and it will also be posted to ptonline.com. Thank you, and have a great day.
Thanks, Heather.
Thank you.